So we'll start chapter 3, processes, and that is pretty much the heart of the kernel. A process is simply a program in action or a running instance of a program, which means that I take a program and I run it, it becomes a process. For instance, I click the notepad icon, so a notepad process is created. I click it once more, one more notepad process is created, so on and so forth. So we'll again have 4 sub parts of this chapter. We'll have the concept, then we will talk about the process descriptor, which is essentially the way that Linux stores all the information about a running process. So we will see that data structure design plays a very crucial role in OS design. It's not that much about algorithms as one would think. It's more about how information is represented. So we have never thought of this to be a very serious problem, but that is true because in a class we do simple assignments. But something as large as an OS, merely representing information is quite a challenge. It is in fact in some cases way more challenging than the algorithm itself, which is straightforward. Like for example, algorithms on trees and stacks and queues, we all know that, and those can lock, stock and barrel be used. But representing information is clearly a challenge. We will look at kind of the unique and some may say unconventional way that processes are created and destroyed. So we will look at what is a process, a zombie process, dead process, so on. And finally, how do we switch between processes? Because there are many kinds of context switching, and context switching is pretty much like a liver transplant. It's a very, very elaborate process where a lot of small actions have to be done in an exact sequence. Even in the sequence, 2 things are interchanged, the entire process may break down. And kindly understand that unlike other operating systems, Linux runs on every piece of hardware. Right? Any new hardware designed today, it is unthinkable that it will not be Linux compatible, which means it has to be compatible with its context switch mechanism, and the mechanism has to be very generic. So we'll look at it. This itself is an engineering marvel. So as I have said, a process is a running instance of a program. It's a program in action, and a program in action has a life of its own, which means that it owns state, it owns files, database connections, network connections, and it also is associated with a lot of additional data structures. So it has a life of its own, and it also has property of its own. So the moment a process is killed, all the property that it owns has to also be released, right? And the thing is that tracking all of this information is difficult. What exactly does a process own? Clearly it owns some access to the CPU in terms of guaranteed CPU time in the future and the amount of time it has taken in the past. The latter for bookkeeping and the former for ensuring that the process runs. Then memory, open files, network connections, so on and so forth. So we have already talked about how processes communicate with the OS in chapter 1 that we have. So we looked at system calls, which is a fake interrupt mechanism of actually talking to the OS, and we have looked at reverse system calls, which are signals. So signals are methods by which the OS sends a message to a process about something. Right, so we'll look at the different types of processes. So processes can either be standalone in the sense they are not related to anybody. So well, processes in a sense are related and in a sense are not related. So let me slightly clarify. So Linux actually organizes all the processes as a tree. So there is one like mother process known as init, and the init process basically has many child processes, they have child processes, so on and so forth. So then they are organized as a tree. But let's say you consider any child. The child may be standalone. Standalone means it comes, it executes, it goes. Or it could be in a group of processes, right? So it could be that, so standalone is also what is called a single threaded process. In a sense, it runs on one core, its job is done. Or it could be related to 5 or 6 or 10 other processes. In a sense, all 10 collaboratively solve a problem and they share a part of their address space. They definitely share their code. The heap they share, the stack they don't share, and some other sections they don't share. But the data says, I'll tell you what they share, what they don't share. So the shared part is basically the code, the heap, all the global variables, which means data, BSS, and so on. This part is shared. The not shared part is the stack, that is not shared, and the thread local storage, which is a small storage region that you can index off a segment register. That part is not shared because the name is thread local storage, right? So this process group where you have multiple individual processes, where and part of the address space is shared. And why is it shared? It is shared such that all of you can collaboratively solve a problem. That is why you share the code, and you have to share the data, otherwise how do you collaborate? And the data is shared of the heap section, and heap is where calls like new and malloc store their data structures. So such sort of a grouping of processes is possible, and each such process that is part of such a grouping is called a thread. So it's called a software thread, right? And that is, a software thread is always part of some sort of a grouping. Of course, you can say that any standalone process is a single thread. That's a fair enough statement to make, but it is not part of a multi-threaded process. A multi-threaded process is nothing but a set of processes where each process is a full process in its own right, but the OS maintains the information that it is part of a group, and certain memory regions are shared across groups and certain other resources as well, which may include CPU time depending upon the scheduler that is used. So essentially the group has some resources that are common to the group, but every thread is a process in its own right. And as I said, threads share the code section, they share the heap, they share the global variables, namely data and BSS. What they do not share is they have a private stack and a private thread local region, and they run on different cores. So obviously the rest of the core specific state like registers and so on, that anyway can never be shared. So broadly speaking, a multi-threaded process contains these multiple threads of execution, where a thread is also known as a lightweight process. So is the difference between a process and a thread well understood? That a process in general is a running instance of a program, and a thread is essentially like a process plus more. And that plus more is that it is part of a grouping where part of the memory space is shared, and the group itself could be the owner of some resources which are shared with all the member threads of the group. So threading is an interesting and important concept because that allows you to write parallel programs. Otherwise, how would you write a large parallel program? Because then you would sort of be constrained to one core. If you have a multi-core processor with, let's say, 4 cores, then how will you use all of them unless you can do a collaborative effort, right? Let's say you want to run a web server. So a web server's job is to basically serve websites, but they should not be separate processes because there is so much in common between them. That is where a multi-threaded architecture somewhat benefits. So given that we have looked at the overall concept, this was a short introduction. You'll find more in the book, and we'll also discuss this kind of ad nauseum. We will, and ad infinitum, we'll discuss this, don't worry. So the key part, the key data structure in Linux is the process descriptor. And as I said, creation of the data structure is the main concern, right? How do you represent so much of information where a process can be standalone or it can be part of a multi-threaded grouping? So we use struct, task struct, which you can see in include Linux shed.h, but we'll anyway cover most of it. And what we are focusing on is how to represent information, right? What are the main strategies? So we are not that concerned with which member does what and which is an int, what is a float. That is not of concern. What is of concern is that this information has to be represented. What is the main strategy? So the strategy is that a lot of bookkeeping information has to be maintained, a lot of regular information has to be maintained, and a lot of relationship related information has to be maintained. For example, a process would have a parent, it would have a bunch of children, right? Because a process starts new processes, they become its children. So it will have a bunch of children, and the process could then be part of some sort of a multi-threaded grouping. All right. So even that information has to be maintained, that am I a part of a thread group, right? If I am part of it, so every thread group would also kind of have a leader process, and all this information we would like to keep in one place. So it will become a reasonably large data structure, but that is all right. We want to keep all such process related information at exactly one place, which is our aim. So we will next look at methods to represent this information and the data structures that are used. So you will find appendix C of the book where data structures are introduced to be quite useful in this discussion. So now we will discuss a process descriptor. So a process descriptor is a data structure to maintain all the information about a process. And as we have discussed earlier, maintaining the information is a very important and critical problem, because otherwise the algorithms to process it are reasonably straightforward. But it's just how to maintain so much of information in one place and make it accessible, that is a challenge. So Linux has an Apex data structure called a struct, task struct for this. And since it is a C based program, it's not a C++ based program, so you do not have classes and objects, but you have task structs. And the task struct is, so you can browse the code, it's in include Linux shed.h. So that will basically, it will tell you the entire structure of the code and the structure, right, how it works. So here are the major fields. We will discuss the fields one after the other. So some of these fields are not used, okay, so it's not that all the fields are used now. Some are not used. So for example, the thread info field, which you will see, it used to be important. It was to maintain low level information. That's not used a lot now. But still, it would be nice to see historically how it was used, because it embodies a design pattern. Because many times when you're writing a program, we don't care about efficiency. So we don't think about cache line boundaries. We don't think about page boundaries. But when you're writing a real program, all of these things, the interaction with the computer architecture, that becomes very important. Because after all, the final thing that matters is I start a program, pretty much I start a stopwatch at that point, and then I end a program, and then how long it takes. So for me, reducing the time that a program takes to run is of vital importance. So that is why anywhere that efficiency can come from, most welcome. So in this case, we will look at subsequently look at the process state. We'll look at things like the kernel stack. So what happens is that for every user level program, the moment it goes to the kernel, it has some state in the kernel. So because the point is, it is assumed that you are running something in the user plane, then you will go to the kernel to get a system call serviced. So then there has to be some place where some of your information is like kept in the kernel. So assume that I am frequently traveling between Delhi and Bombay. So it does make sense for me to have kind of a temporary home in Bombay where I have some furniture and some belongings, right? So think of it this, that let's say most of the time I spend in user space, but still I'm a frequent visitor to the kernel. So I should have kind of some mini home in the kernel where I have a little bit of state. So that mini home is like a kernel stack, and that is required. So as I said, that's common. Whenever you visit from, let's say, city A to city B, if you visit once in a while, you stay in a hotel. But if you visit very frequently, then it makes sense to invest in a small apartment there. That's exactly what the kernel stack is doing. And we'll also see that there is a kernel thread which is like your kernel avatar. So it does the entire system call work for you. In a sense, it's like you're in a mirror image inside the kernel that does the job for you. So we'll discuss that. Not now, but in chapter 5. Then priority information, and then how Linux manages memory. This is very important because we will discuss some novel data structures in that space. Then how Linux manages processes. This is also important because what happens is that every process has a number and it has a data structure. So managing the number as well as managing the data structure, that is complicated. So we will discuss this. Then, as we have already said, processes are organized as a tree. So the mother process is the init process, which is started at the very beginning. And then pretty much init has a set of children. This process again has a set of children, so on and so forth. So they are organized as a tree. So whenever you have a tree, you have parent-child relationships and you have sibling relationships. All right. So we will look at this. And then finally, other fields related to file I/O and device I/O, synchronization, scheduling, everything of that nature. So a lot of state is actually going into a task struct. And this is like one place where you want to maintain everything about a process. And given it is one place, things can go out of hand. But we will see how Linux has sort of not allowed that to happen. And this is the advantage of studying an open source operating system. You figure out how things are actually and really done, as opposed to how they should theoretically happen. All right. So the first question that we would like to store is that, let us say I'm running a user process. Okay. So I'm running a user process. An interrupt comes. When an interrupt comes, I go to the kernel. So far, so good. So then you know the usual sequence of activities. The entire state is collected. The state is put into the context is stored. After that, the interrupt handler runs, and then you decide what to do next. Do I resume that process or do I run something else? This part you know. So the question now is that I would like to know, after I'm done with servicing the interrupt, what was the ID or the pointer to the task struct of the previously running task? That is something I would definitely like to know, that whom did I interrupt? That is also required for collecting and storing the context, but this is something that I would need several times. Who did I interrupt? And whoever I interrupted, where should I keep its state, so on and so forth. Because ultimately I want some pointer to the task struct of the task that I interrupted, and that has to be on my fingertips. So that is why here I'm giving an old solution which is not used now, but let us appreciate the nuances of that solution before we actually move forward. So there used to be a data structure called thread info, and it is a low-level data structure. What does that mean? So a high-level data structure would be a regular structure with int, float, double, and so on, where you would only think of it from your point of view. That I want to store 2 integers and 3 floats and so on, so you just write them down. Int A, int B, float C, D, E, whatever. Give the variables any name that you want. You are not concerned about how it is actually stored. where it is actually stored. Is it aligned to cache lines? Is it aligned to pages? Right? But the moment you are designing a low-level data structure, you would define the same struct, but you would be aware of all of these aspects that I discussed. Right? How it is stored, where it is stored, and what is stored within it, in the context of optimizing its efficiency when running on real hardware. So thread info looks like a regular structure, but as I said, a lot of thought has gone into designing it. So there are two long fields which basically store flags for the current state of the process, the state of the system calls, and synchronization related information. So you have some of these flags. The flags are these 1-bit fields. So what is the most efficient way? So let us say that I want to store 10 flags where each flag is 1 bit. What is the most efficient way of storing these flags? So as we just discussed, if let's say I want to store 19 bits, and where there are 19 flags, each flag is 1 bit each, and I want to store them, then the most efficient way is just store them in a uint 32, which is essentially 32 bits. It's a 32-bit 4-byte integer, and simply say that the ith bit is the ith flag. So this is an example of low-level thinking, because ideally, what someone would have done is just created an array of 19 integers. But 19 integers take 19 times 32 bits. That is a lot of storage, right? That is clearly inefficient, which is not the best way to do things. So the better way of doing things is store all of them in a single integer, and it's an unsigned integer, so 32 bits, and you can store 32 single bits. Each one of them is extractable, again using simple Boolean operations. Boolean operations and shifts, you can extract any bit that you want, simply using Boolean operations and shifts, which is something that the OS code uses extensively. So that is why whenever I want to store a lot of process specific and hardware specific flags, so it's not necessary that every flag is 1 bit. A flag could be 3 bits also, but you are essentially looking at a collection of bits. So if you have, let's say, 32 bits, then maybe these 3 bits, these 3 bits, right, can be stored here in that 32-bit field. Bit number 27 can be stored here. So you can store all of them very nicely in a regular integer. You don't need any other specialized data structure. That is precisely what is used here, and this is an enduring pattern. You will see the same pattern everywhere. Then there is a simple 32-bit integer for the status, and on which CPU the thread is running, right? So the thread info captures some flags, the status of the process, and on which CPU it was running. So this gives us some insight into low-level thinking, that what I could have done, which would have been inefficient, is for 7 flags have an array, just define something unsigned int 7. That would have been royally inefficient. So I chose not to do that, but instead use this bit level trick. So any advanced data structure, let's say in C++ or something, ultimately uses tricks like this, but since Linux is in C, you get to see the implementation kind of bare and raw. So we will now discuss, so the thread info was, as I said, the old way of doing things. We'll discuss the new way, but broadly speaking, the thread info does talk about the state of the process. So let us look at the state of the process, and then we will come back to thread info and how it is stored again. So the state of the process is something that is of vital importance to us, and it's a very fundamental concept, which is why any process descriptor would kind of have it at the very top. So any process, its state, so it's internally actually for these processes, they are called tasks in Linux, which is why it is task struct instead of process struct. So let us understand its states. So we will get a chance to revisit these states several times. So in case you are not able to understand 100%, do not blame yourself, because some of these are slightly tricky concepts. But since we'll be seeing it over and over again, you will get sufficient time to revise and recapitulate. So task running basically means that either the task is currently running or it is ready to run. So what Linux does is, for every CPU, it maintains a queue of tasks known as the run queue. Run queue means that I am ready to run, but of course at one point of time only one task can be running on the CPU. So clearly I am ready, but I am not running, so still my state is task running. Or if the scheduler, so we will consistently use the word scheduler, not scheduler, if that has allowed me to execute and I am executing, my state is still task running. And there are other variables that indicate whether I am running or not, but we will see that setting the same state task running is actually beneficial, because it will not require many state changes, right? So task running means either I am ready to run or I am currently running. All right. Now let us say that if I am running but I get preempted, in the sense a timer interrupt comes, then the scheduler thinks that I have already run for too long a time, so it is time to give others a chance. Then I will get preempted. The moment I get preempted, then I go back to the run queue. My state still remains task running, right? My state does not change, it still remains task running. And that is how I operate with these two states. Now assume that the execution finishes. So here again, there is a little bit of a complexity. So if you think about hardware, what does the hardware know? The hardware is simple, naive and dumb. Correct? All three. The hardware simply sees a program counter, reads the instruction, does whatever the instruction tells it to do. If the instruction is a branch, it will jump to a new location. So the hardware never knows when a program finishes. The hardware has no way of knowing. Of course, you can say that, it's like a plane automatically stopping on a runway. You can say, I'll not stop the plane, but let the plane crash, but that's always a bad idea. Correct? So that's why you should stop before the runway ends. In the same manner, there is no way for the hardware to know that a program is finished. Correct? So now you will say that I write a program and then I write a main function, and in the main function I put one curly bracket, another curly bracket. The moment it reaches here, I'm done. That's what you're going to say. Fair enough, but the point is, when I'm compiling, my compiler actually adds a lot of additional code that you have not written. That code is added both before the main function and after the main function. Before the main function, to set up the memory map, copy all the constants into the memory image. And after the function, the most important being that an exit system call is made. So the program notifies the operating system via a system call that it is done. So the program declares that I am done. And this declaration is made by invoking an exit system call, because the hardware has no way to know when a program has terminated. So I let the OS know. That's the most important thing. So I, as a program, let the OS know that, look, OS, I'm done. Then what happens is that, and in some cases it's possible that there was an exception, so the OS decided to terminate me. I was a bad program, so I got terminated. In both cases, I become a zombie. So task zombie is like a ghost. So a ghost, as you know, is not fully dead, it's not fully alive, right? So I become a zombie and I remain there. So the question is, why do I remain there? The reason I remain there is because the moment a child process finishes, the parent is informed that the child has finished. Now, in the exit system call, I send an argument, which is an integer. In general, the convention is that if the integer is, let's say, 0, it means all well. And then for different kinds of error codes, for example, if I send a negative value or something, it means there has been an error, right? In some cases, even positive values can indicate different kinds of conditions. So I basically send an integer, and my parent's job is to collect that integer from me to understand was I successful or not. Only after that does, in a sense, a task attain salvation. In the sense, from a zombie, it is finally released. So the question is that at the end of the main function, if I write return 0, what exactly happens? So what exactly happens is that in any program, the main function is the main function from the point of view of the programmer, but not from the point of view of the executing code. The OS adds the compiler and the linker, they add a lot of additional functions. So then, so there are many functions, we'll say underscore start and so on, so on. The main is one of those functions, and finally it goes back. Ultimately, a call to exit is there. A system call to exit is there. That is what terminates the program, because the program has to notify the OS that it is done, because there is no way for anybody, including the OS and hardware, to know that the program is done. Once a program is done, it remains as a zombie until its status is conveyed to its parent and its parent acknowledges. That is when you can think of, in a spiritual sense, the program attains salvation, and from a zombie, its existence is finished. Correct? So this is a way of process termination. The other is that I can explicitly stop a process. I can tell a process that, look, you are stopped. So this can be done by sending it the sig stop signal, which is a special signal to just stop it. So this is not something that you handle. Of course, you can type Control Z, which sends it a different signal, which can, so I think this is the thing, sig TSTP or sig STP. What happens is that in this case, it does not have the same priority as sig stop, but the process basically freezes then and there, and then it remains in the task stopped state. It will remain there forever until a signal called sig cont is sent to it to resume it. So sometimes the fg command in Linux does that, or you can send a continuous signal and then it will start resuming. So this is the basic broad idea. Any questions? So the question that was asked is that after Control Z, what happens? So basically, the moment you send it sig stop or any associated signal, the process freezes right then and there. And sig cont is like a way of resuming it. So there are many reasons why you would like to freeze a process. Maybe the process is waiting for something else and that other event has not happened. So that can happen. So this is more like a user generated thing. Sometimes what can happen is that the process initiates some IO, like it tries to read a hard disk. That can take a lot of time because the process runs on a processor which it runs billions of cycles per second, but a hard disk is much slower. Its latency is in milliseconds, which is millions of cycles. So what will happen is, it is important that when I run something which has a long latency, I need to go to sleep. So there are two kinds of sleep: interruptible sleep and uninterruptible sleep. Interruptible sleep means that I can respond and react to signals, right? It's kind of like a light sleep, where it's true I'm waiting, but you can send a signal to me, I can process it, I'm at least partly responsive. And uninterruptible sleep means whatever you do, I'm not going to wake up. Unless the OS tells me to wake up, then only I will wake up. Unless the OS forcefully wakes me up, which basically means that I wanted something and that something has happened, then only I will wake up, otherwise I will not wake up. And you send me any signal, I am not going to respond. So I hope that the process states are clear, because this is a fundamental concept in all operating systems, notably Linux, but of course, as I said, in almost all Unixes and Linux, and to a certain extent Windows also, but given that is proprietary, I must admit that I don't know much, right? I only know whatever Google will tell me, which is not much. So whatever I say about any proprietary OS, that should always be taken with several kilotons of salt. But with regards to open source operating systems, they follow the POSIX standard. And the POSIX is a worldwide standard which sort of defines the standard of the interface. So a lot of them follow the same overall structure of system calls and ways of methods of interacting with the OS. So given that process states are understood, we can just quickly take a look at them once again. So we have anyway discussed this. There is an interruptible state, and so the process can be woken up to process signals, but in this case it will not wake up regardless of whatever you do. The other thing is that in the zombie state, once a process calls the exit call, so once, let's say, I call the exit call, I become a zombie. So the parent process is informed with the sig child signal. So this is sent to the parent. The parent is supposed to call the system call wait to read the value that the child is sending. So the child would be sending an exit value, right? To read the value, the parent is supposed to call the wait system call. The moment the value has been received, right, so the moment the child's exit value has been received, the parent can resume and the child is finished. Resume after the wait system call, that is, and the child's state is completely cleared up. So this is done such that there is still some amount of synchronization between the parent and the child, such that even if a child exits, its value, the return value, is there with the parent. So we thus observe that there is an interaction between the parent and the child, which is sort of underscores the fact that we have a hierarchy of processes, where for the user level, at least init is at the very top. Then whenever you spawn a new process, spawn means create, that becomes your child process. So more about process states. So as we have discussed, there is no way for a process to kind of terminate without calling the exit system call, unless it is getting into some exception condition and is being forcefully terminated. So it still has to let the OS know that it is done. If the exit code is 0, it means that all well, the process executed successfully. This is more like a convention, but a lot of kernel tasks and so on kind of use this more as a rule. But think of it as sort of between a rule and a convention. Otherwise, the exit code indicates the type of the error. One refers to a non-specific error, means something happened, but I'll not tell you exactly what happened. Any other value will give you the precise reason for the error. For example, let's say if it's 19, then 19 would correspond to some error code. So you can look at this file erno.h, which is essentially error number.h, and for a lot of standard calls, it is defined that if this is the error value, this is exactly what happened. Some stand for illegal instruction, some stand for illegal memory address, so on and so forth. Furthermore, what we have said, that the parent has to invoke the wait system call to read the status of the child. Unless the parent reads the status of the child process is not going to get salvation. So see, there is salvation even in the world of processes as well, that even after finishing, you remain as a zombie until this little process of sending your status and the parent recording, that is not done. Only after that can the OS clean up the state of the process. And it's a tree, so every process has a single parent, typical property of any tree. So the stopped state, as we have said, is very interesting. It is there to pause a process, and you can do that from the command line itself if you have the permissions. So let us look at the kill command. So the kill is both a command and as well as a system call. They do the same thing, which is that send a signal to a process. Alright, so that is what the kill command and the system call do, which means that you tell the process ID, which is a number, and you essentially tell it to send a signal. The moment I send stop to a process ID, of course I can't stop a kernel process if I'm a user, but if there is, let's say, another process which I have run, I can stop it in its tracks. So then this will suspend the process. I can also send Control Z on the terminal, and that would send the TSTP signal. Unlike sig stop, this signal can be ignored. I can decide to ignore this signal in the sense that I can just say that, look, fine, you send sig t stop, but I'll not do anything. That option is available to you. Otherwise, the process is suspended if I decide not to ignore it, because ignoring is an explicit act. Then later on, I can use the same kill mechanism to send it the continuation signal, and then the process that was suspended will get resumed. The FG utility, FG stands for foreground, right? So anything that is running is called foreground. I can foreground a process, which means take it out of a paused and suspended state into a running state. All right, so that is something that I can do. So before we go into the kernel stack, let us look at this diagram. Let me clean it up. Cleaning it up is essential. And in this case, if you look at the set of processes, so then we look at this diagram again. So now these states should be more familiar to us, right? So the states here, we should see the running states, we should see the zombie state, the stopped state, and the interruptible, uninterruptible. These happen if, let's say, you are doing some long running IO. And in many cases, if you don't expect any signal to be sent, you can very well go into an uninterruptible state. Or let's say that even if a signal is sent, the signal handler will depend upon the results of the event that you are waiting on. In that case also, it has to be an uninterruptible sleep. So that is your choice, but broadly speaking, these are Linux's states.
In the next lecture, we will discuss how the kernel manages its stack, and then we will move on to discussing process priorities.